First of all, I would like to thank organizers for giving me opportunity to be part of this wonderful program. I have been asked to give a brief overview of technosignatures. So over the next 20 minutes, I would try to give you a glimpse of fantastic research being done in this field as we search for the signs of extraterrestrial life in the universe. We are trying to ask one of the most fundamental questions, and that is, are we alone in the universe? And how do you understand or how do you answer this particular question? The only way you could answer this question is by searching life. What do I mean by searching life? I have to search for signatures of life. These signatures of life are basically divided into two parts. One is coming from the primitive life called as biosignatures, and look for the talk by Litton just before the lunch today. Whereas for advanced life, the signatures are called technosignatures. So what are the technosignatures? The definition of technosignature is this: any science of technology that we can use to infer the existence of intelligent life elsewhere in the universe is a technosignature. Now, how do we go about finding those technosignatures? What exactly are the technosignatures? So a very general two-step guideline is following. First of all, you assume a class of detectable technosignature, hopefully motivated by the life on Earth, and then come up with a better search strategy for these technosignatures. But then, can I just assume this as my technosignature? Can I just say, like, I want to find unicorns in the space thrown by some advanced civilization? Now, you being civilized audience, if this is my hypothesis for a technosignatures, you would probably not call me mad or throw shoes at me. Rather, you would tell me that this hypothesis is neither reasonable, nor you can come up with a search strategy to search for unicorns in the space. So then what decides the good hypothesis and good search strategy? So that was a part of discussion in 2018 NASA technosignature workshop. And then later on, Sophia Sheikh combined the discussions and came up with a formal paper where she has discussed about 9 axes of merits for search. So what you are seeing here is, like, first 5 axes, the horizontal lines are the merit of axis for hypothesis, and the next 4 axes are merit of hypothesis, merit for search. So now, where do the best ideas lie? The best ideas basically lie here. So let us look closely into it. So for hypothesis, the hypothesis should be such a way that your technosignature should be information rich. So if you detect a technosignature, it should tell you more about the advanced life, which is giving rise to that technosignature. It should be an inevitable in the evolution of an advanced life. It should be highly unambiguous, should be very low extrapolation from the current tech, and it should be long-lived, otherwise your searches would not be very sensitive. Now, for the 4 axes of merit for searches, this is basically, all of you are familiar with this one. Whenever you are doing FRB searches or pulsar searches, you are following the same common sense logic here. First of all, the objects that you are looking for should be detectable. Search should have many ancillary benefits. That is why many people are going for commensurable surveys. Search should be cheap, and search should be done now in the sense, like, in a decade or 2. If it is far away in the future, it doesn't make sense to think about it. So now, once we have this thing, I want to give you an overview of the technosignature search in the field, but I want to more focus on this axis, the extrapolation axis, which is shown here, because this is where you can come up with an interesting technosignatures and see, like, where exactly the technosignature and the search strategy fall on this 9 axes. And basically, I'm going to talk about 3 kinds of technosignature: very low extrapolation, somewhere in between the high and low extrapolation, and very high extrapolation stuff. So let us talk about the communication, which is the lowest extrapolation from the current tech. And this was basically the start of Radio City. So hypothesis here is the advanced civilization wants to communicate with us. Or even if they don't want to communicate with us, we can still detect their leaked communications or RFIs. I know most of you here hate RFIs, but you need to know very well what kind of RFIs you are seeing in the radio data, so that you can distinguish between any communication from advanced civilizations. So what are you searching for? We are basically searching for narrowband non-natural radio signals. And this was the origin of Radio City. The genesis started with Project Ozma, led by Frank Drake. He looked at two stars using a 26-meter Tetzel telescope for 150 hours around 1420 megahertz. Of course, the results are none. He did not find any narrowband signal which could tell us about the communications or RFIs coming from the extraterrestrial civilization. But the story doesn't end here. In fact, now we are, with mostly privately funded research, we are searching for stars and galaxies in varied radio bands. For stars, we are looking for interesting stars such as Variable 1, having very large infrared access or having planets in habitable zone. Or along the Schelling focal points, I have a slide on what exactly is this. If time permits, I'll talk about it. And then you can see like there are many, many papers. I'm just listing few of the papers which are published in last 10 years. Galaxies also, you can look for nearby galaxies for sure, but you can also look for some anomalous galaxies. So for example, this paper, Gray and Moule, looked for 2 galaxies with JVLA. Whereas other 3 papers are looking for thousands of galaxies, thousands of nearby galaxies. In fact, one of the experts is in the audience here. He is part of many of the papers. So if you have any questions regarding this, feel free to ask Vishal. What about other electromagnetic band? Why can't you use lasers? It's very easy to see that lasers are the one which are very high efficient, very energy efficient, as well as they can send data which is like 1,000,000 times more bits per second than the standard radio signals. And then if you look into the laser power as a function of time in the lab for continuous wave power, you see that it is basically following the Moore's law. It's doubling every 20 months. And now we are very close to having the 1 megawatt, just 3 years ago, 1 megawatt very stable lasers in the lab. Then why are you not using for communication, or why are you not searching for this in communication? In fact, if you do a simple calculation, 1 nanowatt pulse of laser over just 1 nanosecond focused by 10-meter aperture, you can detect this up to 300 parsec. It can outshine the host star and in that narrow band where the laser is shining. So that is why like people are looking for this one. So the technosignature origin is either direct communication or interstellar communication, or maybe something like beamed energy proportion, which is planning to be used for Breakthrough Listen Starshot project. Those of you who don't know about it, I would recommend you to read about it. So if they are using beamed energies, you are using basically lasers for propulsion. By chance coincidence, you can just detect those. And the idea is to search for transient monochromatic line. So people are working on this. When people realize the lasers are the powerful ways to communicate. In the Marthi and Telis, they are using very small telescope. Over the last 10 years, they have searched nearby 5,000 stars. And they have a detection threshold of like 70 gigawatt laser, having diffraction limited 10-meter aperture up to 1 kiloparsec away. You should also look for this paper, which is where the 13,000 sun-like stars were searched. In fact, people are building big instruments, big surveys with small instruments, such as OSETI, PANOSETI, and LaserSETI. In fact, the Cherenkov gamma ray telescopes are nothing but optical telescopes, which is having very high time resolution. It's because you're basically looking for the Cherenkov radiation which falls in optical band, and then you have different arrays of optical telescope to find out from where exactly the signals are coming. So even the gamma ray telescopes are being used for the SETI work. So I'm going to focus, just show an example of LaserSETI. So LaserSETI is a project by SETI Institute. Currently there are 3 observatories running. They have very tiny observatories. They have like 2 boxes having two small cameras here with a very low resolution spectrograph. And then you can see like they're looking like these two cameras are looking at one direction, exactly 90 degrees to this. These two cameras are looking at another direction. This is to search for polarization because lasers are supposed to be highly polarized. Additionally, there are two cameras, exact same cameras, so that you can distinguish between the cosmic ray hits. And then what they are looking for is nanosecond pulses in optical. The fourth such setup was installed recently, just last month, and this would have a coverage of 40% sky. And this is the point about shelling points, but I don't think I would spend time on this. But feel free to ask me about this at the end of the talk. So where does the direct communication in any electromagnetic band, including radio, stands in the 9 axis of merit? So as you have already seen that this is very low extrapolation from the current tech, but it is also very information rich because if you see a signal, then it tells you more about the advanced civilization. The idea is if it is direct communication, the signal would have more information. It is highly unambiguous, and search can be done right now. Search is also cheap, and people are basically looking for commensurate surveys so that it can be even more cheaper. There are few things like it is little contrived. The direct communication can be very short-lived, and probably there are no more ancillary benefits of those searches. Now going from the direct communication or the low extrapolation, let us look into the technosignature which fall in the middle of this axis. Now this is where we are talking about technosignatures from the atmosphere of the planets. So you can come up with an idea like you can search for nuclear waste spectrum. So for example, lanthanides and actinides are the byproduct of the fission reactions. So you can try to search for this. In fact, there is one star. I'm not able to pronounce the name of the star. This star has a very high concentration of lanthanides and actinides. You can also try to search for CFCs in the atmosphere. And for a star like TRAPPIST, where we have like 7 planets, the TRAPPIST-1e with JWST can find the level, the Earth level CFCs with a signal to noise ratio of 3 with 100 hours of integration. If it is 2 times the CFC level, then you can also get 5 sigma detection with JWST with 100 hours. There is another interesting signature that you can look for is the NOT in atmosphere. Nitrogen dioxide is a byproduct of combustion of fossil fuels and industrial waste, and you can look for NOT. The issue is like only thing is like you need big telescopes such as LUVAR, which is planned 15-meter space telescopes. For there, like you need 400 hours of integration to basically detect NO2 in the atmosphere up to 10 parsecs. You can also look for the detecting city lights from exoplanets. This is a collage of nighttime images taken from the sky, from satellites, and then you can see like city lights are really glowing here. You can try to find out what should be the intensity of the city lights if the planet is like if half of the planet is lit or the whole planet is lit. And that calculation was done in this paper. You can see the spectrum of the city lights. It turns out up to 8 parsec, you can use LUVAR or HABEX kind of telescopes. With 5 to 11 sigma, you can detect the city lights from other planets with 300 hours of integration. So now you can see like there is a little bit of extrapolation going towards the highest extrapolation when we are talking about planets which are completely covered with the street lights. So where do this fall on this merit of access? So it's the information is somewhere in between the information poor and rich. The thing is, most of the things which is discussed here and in the literature, atmospheric technosignatures are the inevitable products, and they are detectable now. Only thing is like search cannot be done right now. Only if the JWST gives time for 100-hour integration for TRAPPIST, you need future observing facilities. And now let us talk about the megastructures. So megastructures are basically the highest extrapolation. You can imagine the type 2 civilization in Kardashev scales can build Dyson spheres. And then you can look for the waste heat from these spheres, which would be emitted in the low entropy channels in infrared. In fact, there was this paper last year, which came up with the 7 candidates out of 5 million M dwarf stars. They looked into Gaia, 2, Mars, and WISE. The 7 candidates are basically M dwarf star with very high IR excess. People followed those with radio telescope. They did not find any anomalous detection of anomalous signals from radio, and seems like few of those Dyson sphere candidates are maybe contaminated by the obscured background AGNs. This was a paper published almost 10 years ago. This is famous Tabby star. You can see the normalized light curve has many weird dips. This was the paper which basically sparked interest in the community to look for the explanation here. One of the explanation was that there is megastructure which is revolving around it. People also try to find out other stars, and there are similar stars have been found in a couple of papers. So this is where we decided to work on. So we wrote a code which can basically simulate any transit light curve coming from arbitrary shapes moving around the stars. The code is so flexible that we can even fit the exocomet light curves. And we come up with an object which we call Dyson disk, which is a circular mirror which is moving around the star. You can imagine like the advanced civilization building the Dyson sphere with these circular mirrors. The problem with that is like the light curve looks exactly like a planet. But there is a subtle differences. If you try to fit planet to the Dyson's disk light curve, you find this signature in the residuals. And this is where we are looking for such signatures in the Kepler data. Now, you can imagine like we can generate a library of light curves for different shapes and use machine learning to see what kind of shape it gives. In fact, we have done this, but I will not give you the results here. You look for the talk by Geetika in the next session. And where do the megastructure fall in? Where megastructures are basically falling most of the time in this region. Okay, apart from like it's very high extrapolation on the current tech, and it will be ambiguous for sure. Last slide is basically this slide. Okay, so the summary is SETI research is growing and it's growing very fast. I'm plotting the number of papers written in last 75 years. Those are around 1,700, and 1/3 of the papers are coming only in the last decades. So yeah, I'll stop with this slide, which is talking about the first rule of SETI. I'll keep the slide here and stop.
Sir, there is some disturbance in my phone. So this is the silence component, sir, FPGA, important component. Item number 10.
Sorry.
Yes, sir. This is costing 405 approximately. Yes.
May know who is addressing. Can you tell your name and
who would be here?
Yeah, please go ahead with your question if you are talking from the Zoom connection. I think that was error from some other communication. So please have your questions asked to Vikram. Yeah, there's one question there.
Hey Vikram, nice talk. I was just curious, you talked about megastructures and you searched for the access IR emissions. Are we also expecting some kind of radio emissions from these kind of structures?
That is the idea, basically. So if it is really a Dyson sphere, then the first thing we would look for is some kind of RFI. Okay, because the things are getting built there. Okay, so you could look for some anomalous signature from radio. That is what was searched in the paper, this particular paper.
And
takes time. This Ren, Garrett, and Simeon 2025.
And like, are you expecting some kind of specific frequencies where you should be searching for it? Or like, is it a uniform sampling to every frequencies?
No, that is the most important question. See, it's like searching for advanced life is basically searching a needle in a haystack. The only thing is like you don't know where exactly it is. You don't know when you should look for it, and you also don't know like which frequencies that is where you are looking for it. Okay, so in fact, the idea was like to look for 21 centimeter line initially. The project Osmo was looking at 1420 megahertz. So we don't know. Ideally, one should search for the whole parameter space.
I see. Thanks so much.
Questions for, yeah, so last question.
Hi. Yeah, thanks for the talk. So I was just asking if we are looking for RFI-like signals, then how will propagation effects like affect that? So we can't just look for like direct, like say narrowband or that kind of this one. So
I think the better person to ask is Vishal. He's asking about how will you distinguish between the RFI and the transmission.
The main idea is that you need to try localize. Signal might look exactly like what we produce, but the signature that can distinguish it, whether it is from our technology or versus the terrestrial, is that it has to be silent. So we use various techniques to identify if the signal is coming from the sky or if it's generated by a sky.
So ideally, you look for one region and then you look for another region. If the signal persists, then this is probably the one.
thank you.
I think there is a lot of AI involvement possible here.
Yeah.
Thank you, Vikram. We are moving on. If you have more questions, I'm sure, please catch Vikram later.